like dy by dt a1 y square plus a2 plus a function h of t, okay, and the integral from 0 to t of y of t dt can be estimated by where a1 and a2 are constants. Okay, I'll talk in a moment about h of t, but h of t, okay, we already have said it. So the integral of y of t can be estimated by a constant a3, and the integral of h of t can also be estimated by a constant, say a4, okay, where all of these ai's, are non-negative for 1, 2, 3, and 4, okay. In other words, these integrals are bounded. Integrals of y and h are bounded over the domain of the definition of y of t and h of t. Okay, so these are non-negative constants. Then, so here are some consequences. Then, for any r positive, with r between 0 to t, the following holds. Okay. Following holds. So what else holds? This holds. That y evaluated at t plus r, in other words, that at any instant t after the r, instant r, can be estimated by the same constant a3 by r plus a2r plus a4 times e raised to a1 a3 for t in the interval 0 to t minus r. Okay, I know it's a bit boring, but you will see the magic of this lemma actually. That how this seemingly strange lemma is going to allow you to investigate the long-term behavior of a reaction diffusion equation and also a class of problems actually, a big class of problems. Okay. Furthermore, so if t explodes, in other words, t is infinity, in other words, y and h are defined on a semi-infinite interval, okay, and all this is satisfied for 0 to infinity, okay, then you will have this, but you will have another very interesting property, is that if you take, say, limit t goes to infinity y of t, this y of t will go to 0 as t goes to infinity. In other words, that this y of t is going to converge to 0 in long run. Okay. So this lemma is due to Shane and Zhang. Okay, and so you can find the reference in the notes. They proved this lemma in 1993. I think this was a paper on studying the Kahan-Hillard equations. Actually, it's a very interesting set of equations, and they proved this interesting lemma. So what I'm going to do, I'm gonna give you some high points of the proof of the first next part of this actually. So this furthermore part you have to do it for yourself. So I'll send this paper to you, okay? I'll upload this paper on LMS. You can also find its proof in the book. But you know, I think it's good to read the results from the original sources. Okay. So I'll send you this paper, and you can figure out, or you can read the proof of this part from the paper actually. Okay, so I'll just talk about you know, that the situation that if you have these two inequalities satisfied, if y and h satisfies this condition, then you have this inequality, this strange looking inequality. Okay? And if the same is true for t equal to infinity, then y is the kind of a function that is going to get to the 0 in long run. Okay. So here's a sketch of the proof. Okay, maybe sketch of proof. This is a sketch of the proof. So what to do? You know, interestingly, I mean, if you have encountered, say, the proof of the uniform, say, version of the Grunwald lemma, because I mean, if you remember, the Grunwald lemma says something similar actually. Not similar, quite similar, but you know, it's on the same lines. So if you have the Grunwald lemma, I mean, what would be the interpretation of this result? The interpretation of this result is that if your y satisfies a kind of a quadratic inequality, and you know, the integral of y and h are bounded and satisfies this condition, then the y always stay below this fixed number actually, this number, which is independent of y. Okay? So, you know, this makes this result, you know, a bit similar to Grunwald lemma. Okay? And hence its proof is also really similar to the Grunwald lemma. Okay. So how to proceed? Let's proceed in this manner. So imagine I have an instant s between t and t plus r, okay, where r is this fixed number and obviously t is non-negative. Then what you can do is that multiply the both sides of this inequality by, okay, e to the, so let's multiply the both sides of inequality by a factor, say dy by dt. Okay. Multiply, say, let's call it a star. Let's call these two conditions as double star. Okay. Multiply star by an exponential factor. So this is like integrating factor. Okay. By a function e raised to negative t to s a1, which is fixed, y of tau d tau. Okay, so multiply the both sides of this inequality by this factor. So once you're gonna multiply, let's assume that I have written this exponential here and the exponential here. Okay. Then after multiplication, the inequality can be rewritten as this actually, okay, d by ds of, say, y of s e to the negative t to s a1 y of tau d tau. Okay, let's calculate this expression and let's see what we get. So if you're gonna calculate this expression, so what you're gonna get? You're gonna get dy by ds, product rule, which is e to the exponential from t to s. So this factor, which is precisely this term. I mean, if you multiply the e to the negative integral from the both sides, you're gonna get this first term. Okay, plus what would be the other thing? So it's going to be y of s times the derivative with respect to s of this exponential is going to stay same. So I'm not writing the all details, I'm just putting t to s. Okay, times the integral or the derivative, the s derivative of this integral. And what would be the s derivative of this integral with respect to x? You know, really by the fundamental theorem of calculus or your Leibnizian formula. So if you have exponential of the integral with respect to x and you're differentiating with respect to s, okay, and then what will happen is that this integral will go away and you're going to get negative. So you're going to remain with the integrand actually. So it's going to be a1, okay, y of s, and that's it. So it's a1 y of s. So this is what that you're going to get actually. So a1 is really the constant. Okay, it's like a fixed constant. So what I'm doing is basically I'm applying this result. Okay, so d by dx from a constant a to x, say f of t dt. Okay, if f is a good enough function, then this is going to be simply equal to f of x. So basically I'm applying this result. I have applied while differentiating this integral, I have applied this result actually. So you're going to get this a1 y of s. And if you simplify this expression, so you get an interesting thing, and that interesting thing is that you will get, say, minus a1, and this y of s and y of s will become what you call y of s squared. So if I expand this term, I'm going to get this term actually. Now if you see, this term is really when you multiply the exponential, you know, this exponential from t to s, and you multiply the exponential from t to s, okay, this is really the first term. This is really the first term actually. So what do I mean by that actually? So I can, so in other words, this term, okay, this term minus this term is equal to this term. Okay. So what would be the end result? The end result is going to be, okay, going to be what? So these two terms will be put together into this single term, and remaining is going to be this e to a2 plus h of t minus e to this integral. Okay. So therefore I can say that this can be estimated by what? By okay, so this can be estimated by a2 plus h of s and exponential from t to s a1 y of tau and d tau. So this is what that you're going to get actually. And this factor is smaller than or equal to 1 because y is non-negative, a is non-negative. So this integral is non-negative, but and hence the entire term, the power of the entire term become negative or non-positive. So this is like a term that is smaller than or equal to 1 actually. So I can estimate this by A2 plus H of S. Okay, so you're gonna get this inequality. Okay, so you're gonna get this inequality. So what is the next thing that you do? Now let's integrate this inequality, the obtained inequality from both sides, from say from S to T plus R, okay, with respect to S. So I need to also integrate this S to T with respect S to T plus R with respect to ds. Okay, so this is what that I need to do. Okay, so I've proved inequality, and then let's integrate. So when you're going to integrate, what will happen? So the first term is going to become y. So obviously the result of this integral is going to be the integrand, okay, because this is the derivative, so you're integrating the derivative of s with respect to ds. So the result of the integral is going to be really integrand, and then you need to put the limit into the integrand actually. So when you're going to put the upper limit into this, so what you're going to get? So you're going to get y of t plus r, okay, and exponential from s to t plus r, okay. I'm not writing the rest of the term, you have to assume it. And the second term is going to be what? So in the second term you need to put s. So this y of s will become y of s, and this exponential will become what? S to s actually. So this is going to be a 0, and hence this exponential is going to become 1. So what is going to remain is really y of s. Okay? So let's write this y of s here. Okay? What would be this plus what would be the integral of a2? So the integral of a2 is going to be a2 times t plus r minus s, okay, and integral of s to t plus r with of h of s with respect to ds. I mean, if you remember, we have an assumption that the integral of h of t from 0 to t is less than or equal to a4. Okay, this is less than or equal to a4. So this integral from s to t plus r of h of s ds is also going to be less than or equal to a4, because this is really a subinterval of 0 to t. So I can say that I can estimate this by what do you call a4. I can estimate this by a4. All right. All right. So what is the next thing? So what I have to do, just write these two estimate on your star and double star or your pages, because I'm going to get rid of it, and what? And prove the rest of the inequality. So we are almost there. We are almost there. It is better for such kind of result that you should read it for yourself. Okay? But I'm just giving you hints so that when you read it, you have some sense that what you are talking about. So y of t plus r e to the s to the t plus r y of s a2 plus t to the r minus s, and the integral from s to t plus r h of s ds is less than or equal to a4, so you have it. Okay. you can even further simplify it, because as s is less than or equal to t, okay, so we can also say that s is less than or equal to t plus r. So even in this, okay, so the t can be estimated. Okay, so if t is less than or equal to s, then I can say that negative s is less than or equal to negative t. So even in this part, I can go a step ahead and I can say that since t is less than or equal to s, so negative s is going to be less than or equal to negative t. So I can estimate this negative s by negative t, and this is going to make this a 2 t plus r and minus t actually. So I can write it actually that, okay, this factor is less than or equal to this factor, and which is that now you can get rid of the t. So what is really the final conclusion that you get? That the final conclusion that you get is really this. The final format of the inequality, this is going to be y is going to be this inequality. So if I send this factor on other side, so I can say that so y of t plus r can be estimated by a2r plus a4 multiplied by e to the positive, okay, it's going to be positive, e to the positive s to t plus r, okay, and a1 y of tau d tau, okay, y of tau d tau, and I can okay, so there is going to be another term as well. Okay, so let me write it actually. Put all this together because okay, so we also have this y of s actually. So if you multiply this factor onto the other side, so this would be multiplied by y of s and you know these two terms as well. So we should write it as y of t plus r is less than or equal to y of s plus a2r plus a4, okay, and the integral of e to the s to t plus r, okay, and a1, so a1 is a constant, so I can pull it out and I'm going to have y of tau d tau, okay. Now if you remember the condition from double star that we wrote in our assumptions, there was a condition that if you integrate from 0 to t y of tau d tau, I can estimate this by a3. Okay, so this is always less than or equal to a3. Now this guy is a subinterval of 0 to t. So the same is going to be true for this actually. So I can say that this is same as y of s plus a2r plus a4 and e to the a1, and all this can be estimated by a3. So this is really one of the neat inequality. Okay. But what we don't like about this inequality is that we don't like this y of s actually. So we want to make this side independent of the y of s. Integrate this inequality once more with respect to s. So integrate with respect to s once again between t to t plus r, t to t plus r. Okay, from t to t plus r, from t to t plus r. So what would be the outcome? The outcome of this is going to be that, okay, let's integrate y of t plus r with respect to ds from t to t plus r, okay, less than or equal to, so this is going to kind of get rid of this y of s, and t to t plus r y of s, okay, plus a2r plus a4 e to the a1 a3, and integrate all this with respect to s. So there is no s here, so you can pull it out of the integral, and what you're going to get is really the difference of the endpoints actually. So what would be the difference of endpoints is going to be r. So you're going to have r of y of t plus r. This can be estimated by what? By what would be the integral of this? So by our assumption in double star, okay, of our assumption, the integral of y of s from 0 to t can be estimated by s3. So I can estimate this by a3 plus what would be the integral of a to r? So there is no s here, so it's going to be a to r square plus this is going to be a4 r, okay, and you're going to have a e raised to a1 a3. So this is what it is going to be, okay, that's how it's going to look like, and we kind of got rid of the y of s. So the final inequality that we're going to get is really the y of t plus r, and if you divide everything by r, so you get your one of the required inequality, which is a3 or divided by r plus a2 r plus a4 over a1 and a2. Okay, so this is what it is. Alright, so this is what it is. So this was one of the inequality which was required to prove. So you realize it from the proof that it's not really a difficult proof. It's a pretty much a straightforward proof. But it's not that boring, but it's a readable proof actually. Okay, so if you want to see the details of it, so I'll upload the paper of it. I have already uploaded the paper of it, so read it from the paper by Shenzhen. And your task would be to prove the second part of the paper as well. The second part of the proof as well, that where if you take t to be infinity, okay, the y of t will go to 0 as t goes to infinity. Okay? So this is really it. Now let me write